Hello, welcome to lecture 9a. I'm going to try to start breaking these up into smaller chunks. So the A part is only going to cover the first two of these objectives. And we are going to do classify flow regimes by flow characteristics and the Reynolds number. And so basically what we're going to do is we're going to talk about laminar versus turbulent flow and how you figure out what one is, either by looking at it or by calculating this magic Reynolds number. It's not really that magical or anything, but you know it does its job. So then we're going to classify the dimensionality of the flow, and that just means whether or not the flow is considered one-dimensional, two-dimensional, three-dimensional. For this class, that's kind of esoteric. I'm not really sure that I can think of a good time when you might need to do that for this class. However, if you go into other classes that, graduate school and things like that, it's just about ways to think about the problem in order to simplify it. And then last, I'm going to compute the volumetric and mass flow rate. Those will be lecture 9b. That's just kind of how I think I'm going to split this one up right now. Okay, so we're going to start by, so we're going to kind of break out all of our flows into either laminar or turbulent. And I'm going to put a link to a video where you can kind of just look at these. But laminar flows would be, I'm going to put this in quotes, smooth flow. And the turbulent flow is highly irregular. Okay, so typically like if you watch a laminar flow and you watch like an individual particle, let's suppose you're in a pipe and you see a laminar flow, you're just going to see this particle and it's just going to kind of move along like this. Okay, and if there's one in the middle, you could watch that particle and it's going to go like that. If you're in a turbulent flow, that one little particle, it's going to be all over the place. Okay, the particles are, they're just kind of doing their thing, and they may not even, if one's on the bottom wall, it may migrate up to the top wall, or et cetera, et cetera. Whereas in the laminar case, that could happen, but it would be highly irregular. Excuse me, irregular is the wrong word. It would be unusual for that to happen. The only way, okay, so I guess what I would say about the laminar is that it's predictable. Okay, and turbulent is unpredictable. Okay, in fact, there's this guy on YouTube who's really, really fired up about laminar flow. He does a whole video on it, but anyway. So the shear stress in this flow, okay, is governed by this equation, which we've already learned, governed by tau equals mu du d, whatever that dimension is. I guess in my little pipe that I drew, that could be the radial direction, dr. Okay, and in the turbulent case, so I guess in the laminar case, the key is this symbol right here, this mu, which has to do with molecular exchange. Okay, so basically like a little particle, like if I zoom in, the particle in this row right here, they're going to interact with that one because of the molecules. They're going to kind of, and they're doing that just because of that's not Brownian motion, but just, the random motions of molecules. And it just so happens that the molecular exchange is very, very small. Okay, now if we go over to here, okay, and the particles themselves are exchanging just because they kind of have these jumps, or these what we call sweeps, and they kind of sweep up, and they might have an eddy or something like along those lines. You might be able to imagine that this exchange is much higher. The exchange between, say, this layer here and that layer there is much higher when the fluid motions themselves are going to carry it up that way. It's not just a molecular exchange. So when we talk about the stress in the fluid, okay, and in this case that's determined by this viscosity. Over here, the shear stress, or well, let's just say the stress is much, much higher. Okay, so we have greater stress. Okay, and that's due to greater exchange. Okay, so it's not dependent on just the random motion of molecules. It's actually the fluid itself is moving in such a way to bring the momentum into another layer. Okay, So over here, we could say that the molecular, okay, exchange, okay, dominates, okay, and essentially that's what creates viscosity. And over here, the exchange is due to just fluid motions, okay? So hopefully you can kind of see how the fluid motions might be more efficient at, exchanging momentum or whatever between layers in this turbulent case. And this is like kind of the thing that I think is really, really cool. So due to this greater exchange, so greater exchange, okay, lesser exchange. And what does that mean? Why do we care about this exchange so much? Well, what it means is, so if I look at the fluid profile, and let's suppose a pipe. Okay, so in this case, we have a no slip condition at the wall. So we're not gonna. So in the laminar case, we have no slip condition at the wall, and then it's going to move fastest in the middle. Okay, so that will be whatever U max, I guess. Okay, U meaning velocity in the x direction. And what's going to happen is this thing is going to, it actually ends up being a parabola. Okay, and so basically the flow kind of looks like this. Okay, and now you might say, well, what's to prevent, so if we were to increase the amount of exchange, what would happen is, this higher, well, let's just copy this and bring it over. And that way I can use it as an alternate case. So if I go over here, here's my greater exchange. I'm going to paste it right there. Whoa, that's way too big. Okay, so let's put it on top of the greater exchange, and let's see if I can't delete that word. Somehow I doubt I'll be able to do that. Anyway, it doesn't matter. All right, so as the exchange increases, okay, then what's going to happen is, I'm going to kind of do this in another color. Hopefully you can see the colors. So if we imagine, a fluid particle that's moving along here, well, what if there's greater exchange? So a second ago, these two layers right here and right here, the ones right next to each other, they were pulling on each other, okay? And they were pulling on each other for two reasons. One, because they are cohesive, and so they, kind of pull on each other. And then the other reason is because of exchange. So the faster moving fluid in this thing, in this layer, is just because of random molecular motions, it like kind of swaps out with the one in the other layer. And so when it does that, it tends to speed up the slower layer and slow down the faster layer. But what would happen if instead of it just communicating with this layer right next to it, it had a big, like an eddy? Okay, so now it's communicating with this one over here, okay, and that one over there is communicating with the one in the middle. And hopefully, when you think about that, you realize that what's going to happen is, instead of these two layers right here and right here being pretty close in velocity, these two are going to be in close in velocity because now it's exchanging with over a much larger area. So the particles here, fluid particles here, have that momentum, and they carry it into this slower layer, and so they speed it up a lot. However, this one, it jumps into the faster one, and it slows it down by a lot. So what ends up happening is we end up having, if we draw this over here, we end up having a more uniform velocity profile. So it kind of looks like this. Okay, with this being U max. Okay, and so all through this middle area here, okay, so the greater exchange leads to more uniform velocity profile. Okay, so all in this middle area, the velocity is almost at that maximum velocity. Okay, and in fact, a topic we'll kind of talk on eventually is, you'll notice that, what about these little areas right here? Okay, this is where essentially the flow feels the boundary or the edge. So this is called a boundary layer. Okay, and like right now, you and I are, well, I guess I don't really know how to describe it if you're inside your house watching this, but if you're outside, you're in the atmospheric boundary layer. You're in the area that basically can feel the effect, where the atmosphere can feel the effect of the Earth. If you get high enough up, you kind of get into this area, okay, and you'd say, well, I'm not really in the boundary layer anymore. I'm just kind of, I don't know, I'm somewhere else, okay? So anyway, so what we want to do in order to kind of try to figure out, hold on. We want a way to determine, without having to look at, images of fluid flow. By the way, watch the YouTube video. I'm gonna post one here. So watch the YouTube video and you'll see. Okay, or if you want to, just search it yourself. Do laminar flow, and then do turbulent flow, and you'll see exactly what I'm talking about. Okay, by the predictability versus the unpredictability. But anyway, we need a criteria that's going to kind of tell us what's going to happen here. And so what we typically do, and I'll kind of go over here. We've got plenty of space. Is we use something called a Reynolds number. So a Reynolds number is named after this guy, Ozzie Reynolds. And it is one of numerous, thousands probably of dimensionless numbers. So it has no dimensions, and it comes out of the equations, and I could pull it out for you and show you where it comes from. But for this class, it's not really important. So it's named after, Reynolds number, RE, and it equals rho, rho times the velocity times L over mu. Okay, and so okay, what is all this? Okay, and so another way to write this is so if you remember your equations from the beginning of the year, these two right here, that's a nu, so that's the kinematic viscosity, and we've got viscosity over length. Okay, so remember this v on top, that's a velocity. This L on top, that's a length. And the length is the hardest term in here. And then the nu on the bottom, that's the Greek letter, and it means the kinematic viscosity. Okay, so a few things, and then I'll start to talk about the magic of this. Okay, so one of the magics of it is that it's dimensionless. Okay, so if I look at the top, I've got if I do the dimensions on this, the top is a velocity. Let's suppose we're in the SI system, so this would be meters per second, times a length, which would be just meters, okay, divided by the viscosity, meters squared per second. Okay, and so all that cancels out. Okay, so the meters and the meters cancel with the meters squared, and the seconds cancel with the seconds. Okay, so so it's just a number. You say, what is the Reynolds number for this flow? And somebody would say, oh, it's 7.2 times 10 to the fifth. Okay, no units. So that's, to me, I rather enjoy that. And one of the things that we typically say with this is we say it's a ratio. So that's one of the things that makes it dimensionless. It's just a ratio of two things with the same units of inertial to viscous forces. Okay, so that's a little bit interesting. And so let's talk about what that means. Okay, so I want to look at it in this form right here. Okay. And I want you to think about momentum. Okay, so typically if something has a lot of momentum, what does it mean? Usually it means it has a lot of mass. Okay, so we've got density, just kind of our mass. It's our mass per unit volume. Okay, and we've got a length scale. Okay, so this is kind of how much of something it is. And then something with a lot of momentum has a velocity. So that's how fast does it move. Okay, so if we take those together, we get a momentum. Or, often kind of referred to as like an inertia. Okay, so this is kind of like the inertia of the system. Okay, and then kind of what's resisting that inertia, or what's causing things to like slow down, would be the viscosity. Okay, so I mean, that's a little bit weird and it's a little bit hand wavy, but you can kind of think of this as the momentum or the inertia, and this as the viscosity. And of course, it can also be written this way, which is the easier way to, this is the easier way to write it. This is the way that usually you'll see me write it. Anyway, so that's kind of what it means when it says it's the ratio of the inertia to the viscous forces. So basically, if this number is really, 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 really large, then what that means is that means that the inertia forces are much larger than the viscous forces. And you can almost look at a flow and you can say, you know what, the viscosity is not important because the inertia, it just has so much inertia that it's just not really affecting things, okay? And, you know, that's a little hand wavy, but, you know, that is the way that these things work. And so, so basically what happens in any given situation, so then, I mean, this is kind of the key right here, or one of the keys, is the hardest thing is this L. What is this length scale? Okay, and what happens is I'll explain to you like conceptually, what you want to use for a length is the length is somehow the length, if you believe that's the word length. You know, it's kind of like an art form to figure out which length you want to use. Sometimes it's defined which one you want to use, but it's basically and this is going to be my words for it, so this is not an official definition or anything, but the length is some length scale that quote unquote determines the size of the largest eddies. Okay, so this is not something that anybody ever told me when I took this class. Okay, but what this kind of means is that usually, and there are cases where it's just defined a different way, but like usually, like let's imagine you were talking about a pipe. Okay, and so well, how big could the biggest eddy in this pipe be? Well, the biggest eddy that you could possibly imagine would be about that big. Okay, so it's essentially the size of the pipe. Well, what length scale matters? Well, in this case, the diameter of the pipe. Okay, you cannot get an eddy bigger than that. Okay, and really the word we want to use instead of determines is we want to say that it scales the size of the largest eddy. In practice, the largest eddy in a pipe doesn't actually get as large as the full diameter. The largest one's usually about 40% of the size of the diameter, so maybe it's like this. Okay, but whatever the case may be, this D is the determining size, right? So if you double the D, like for example, if you got a pipe that was twice as, whose diameter was double, well then this eddies would be twice as big. So the D would be an appropriate scale. So you might imagine that, I suppose you were doing an airplane or something, and the airplane is going through the wind, and you wanted to know if the flow around this wing is laminar or turbulent, or you wanted to use this Reynolds number to figure something out about this. And so you would need to know, well, what length scale do we want to use? Okay, and in this case, it's not really clear what that would be, but one possibility is the length you are along the wing. Another possibility is how far away from the wing you are, and it's going to determine which one of these things is going to determine the size of these eddies. And actually, in this case, I think you will sometimes see one, sometimes you'll see the other. Okay, or if you have a block of wood or something and you've got water flowing around it, say for whatever reason, maybe this is the bottom of your dock or your pier or whatever. Well, the eddies on the backside are going to be determined in part by the width of your pier. So if you wanted to know what the Reynolds number was back here, you might use this size. Okay, now in this class, that's neither here nor there, because in this class, it's always done for you. In that, for example, in this class, we're almost always going to be working in pipes. So in pipes, the Reynolds number in a pipe, okay, is the velocity in the pipe. Really, it's the average velocity. So I'm going to put that line over to mean average over the diameter divided by the viscosity. Okay, so this is for pipes, and this is the diameter of the pipe. Okay, and now does it have to be the diameter? You might say, well, couldn't we use the radius? Of course you could use the radius, right? The difference would be that what happens here is that this Reynolds number is used because it's the ratio of the inertial to the viscous forces. If the viscous forces are really, really, really large compared to or large-ish, then what happens is you get a laminar flow like this because the viscosity, the fluid, there's so much molecular, the stickiness of the fluid, its resistance to flow, etc., that if there were a big eddy, it would be damped. okay? So in other words, this is small Reynolds number because the viscosity is relatively large, okay? Whereas over here, okay, the viscosity is not preventing all these movements in this turbulent thing. So the Reynolds number is large, okay, greater than some, arbitrary number. And so, and the reason for that is because basically if one of these little particles has enough momentum or inertia, it's just going to kind of do its own thing, and the viscosity is not going to dampen its motions, okay? So between those two things, we get the difference between laminar and turbulent flow. And so basically, what we do to figure out if something is laminar or turbulent is, like, let's suppose you're in a pipe. What you do is you calculate this number, and if the Reynolds number is in a pipe, and different books will use different values for this, but usually it's about 2,000. Okay, then, or I think let's go with 4,000. Okay, then it's turbulent. Okay, if the Reynolds number in a pipe is less than 2,000, it's laminar. Okay, what if it's in between? I hear your brain asking, what if it's in between? Well, if it's in between, you're just in some sort of traditional transitional flow. And, it could be either. It kind of just depends on whether or not something trips the turbulence, something like, there's something in there to create a little turbulence, and once there's turbulence, it kind of like unfolds and just keeps being more and more and more turbulent, okay? Now, what I want to make clear here is that these numbers right here, this 4,000 and this 2,000, these are not, this is for a pipe. This was determined empirically. Somebody did a bunch of studies, and they determined that when the Reynolds number as defined this way, using the diameter, and this is why we use the diameter, somebody determined that when they use the diameter, Reynolds number in a pipe about 4,000 is turbulent every time. Okay, and if you get Reynolds numbers less than 2,000, it's laminar every time. Okay, if you wanted to define your Reynolds number a different way, and you wanted to, let's just imagine you were like, I don't want to work with this, I want to work with the radius. Okay, you could do that. Okay, it's still dimensionless, it works in every way, but what's going to happen is, well, we're going to go down here, and this is no longer 4,000, right? Because I just kind of divided my diameter by 2, so this is going to be 2,000, and this would be 1,000 if you were to do that. Now I ask you, why would you do that? Don't do that. Okay, so don't do that. I guess that's what I'm driving at. Okay, you could do that, but usually what happens is when you're working in a particular situation, there's a particular way that we do it, and I just recommend you kind of go with that. Okay, so I don't know off the top of my head what the transition, what the numbers are for like a river, but if you're in a river, okay, and so here's the water surface, and here's the bed, and it's sand or whatever it is, then there's a way that you define this Reynolds number, and usually it's going to be, the mean velocity in the river times the depth, okay, which I'll call h over the viscosity, okay? And again, it's because the largest eddy in this thing is somehow being set by that depth. Clearly, it can't get bigger than the depth. You can't have an eddy that does this, right? So you would use that h, right? And usually you can just look up in a chart or whatever, like what the best way to do that is. And so that's really what I recommend. Okay, so that's Reynolds number. Reynolds number is really most commonly used just to determine if something is laminar or turbulent. There's a lot of nuance in Reynolds number, which we won't really get into in this class. If ever you guys want to talk about it, come to office hours. We could talk about this for days. Okay, so the last thing that we're going to do before I go to lecture 9b is we want to do the dimensionality of the flow. And this is just a simplification. It's basically like all flows technically three-dimensional flows. However, sometimes we might want to simplify it. And you might want to consider a flow one-dimensional. So if the flow is one-dimensional, the reason you want to do this is because you don't want to deal with a whole bunch of other stuff. So you're going to neglect changes in, let's say, velocity, pressure, etc. Okay, transverse to the flow. Okay, so a good example of this is a flow in a pipe. Okay, so if you're in a pipe, okay, this is a pipe. Okay, and we imagine that I made it the same diameter everywhere, so it's the same diameter here as it is here, although clearly I didn't draw it that way. There are differences in velocity going across the pipe, right? This is the velocity profile. It's going faster in the middle than it is on the sides. However, we want to treat this problem as if it's one-dimensional, as if the only thing that's happening is stuff is moving from point 1 to point 2 to point 3, and basically the pressure is dropping along the pipe. But I don't want to worry about the fact that things are a little bit different along these edges, or maybe the pressure is a little bit higher right here than it is right here, or vice versa. I don't want to deal with all that stuff. Okay, so instead we're going to treat the problem as if it's one-dimensional. And so the only dimension is this dimension, right? So we could call that S, or we could call it X, or whatever we want to call it. Okay, so, it's just like sometimes you look at a problem and you go, you know what? I don't want to deal with all the complicatedness of the size. Now, maybe there's pipe problems where you can't do that. There certainly are. But a lot of times you can. Okay, so here's a 2D problem. Okay, so obviously it's kind of the same definition. So we're going to neglect changes in V and P, etc. in the third dimension. Okay, and one of my favorite example for this is flow in a shallow marsh. Okay, because we're Louisiana, we have lots of marshes, although most states have marshes somewhere. And so you imagine here's a marsh, and so it's really, really, really wide. Maybe it's many kilometers wide. Okay, and and the water is just kind of moving through it. Okay, but its depth, the depth of this thing is like, let's suppose it's a couple centimeters deep. So I mean I can't draw that dimension because it's in and out of the board right now. But you can imagine, like in this case, I don't want to deal with the fact that the flow is like at the bed it's not moving, and at the surface it's moving faster. Like you might just say, you know what, I don't want to worry about that. I'm just going to treat it like everywhere. There's no difference between the top of the water right here and the bottom of the water right here. They're just, it's just too much complication for a simpler problem. Okay. I should note that, especially with a problem like this, you can use Cartesian coordinates, as I've drawn this particular one right here, or you can use polar. So, for example, you also might have a marsh where, let's suppose it's a river delta, where the river is, spreading as it enters into an ocean. So we might have a river over here, and there might be an ocean over here. And again, we don't feel like dealing with the fact that between the bed and the surface, there's any kind of variation in pressure or velocity or anything like that. We're just like, you know what? Let's just simplify our lives. Let's consider this a 2D problem. Okay? And I think you guys will probably get to problems at some point in your careers where this becomes a viable strategy. Okay? So then the last one here is fully three-dimensional flow. And in three-dimensional flow, basically you just have to consider everything. Okay? So three-dimensional flow, so flow varies in all directions. Okay, as does flow and pressure and obviously velocity, etc. Everything varies in all directions. Okay, and I usually like to think about this as wind in the mountains. Okay, if you've ever been in the mountains, you've probably experienced some pretty cool wind. But we can imagine a mountain, a mountain range, and it's got a whole bunch of peaks and things. And then you can imagine the wind coming through here and, doing all kinds of crazy things that wind does. I do know some things about what wind does because I know fluid mechanics, but I'm not going to lecture you on how wind moves from mountains because I'm the wrong person for that. But anyway, so as it screams and swirls and does all of its stuff in there, you can see that in every direction and also in time, the wind is constantly changing. So you can have wind going up or down or left or right, and to get a really clean picture of what's going on there, you're going to need to do all four directions. So next up, lecture 9B.